Now we are going to start off with the next set of models and we'll be talking about physical and device models. So these are the models like keystroke level model. It's an example of this type of model. They're based on empirical knowledge of human motor system. The user's task is done in the form of acquisition and then execution. These only address the execution. Complementary with the goal hierarchies. They are in the form of complementary models along with the goal hierarchies. So let's start with the first model of this type, which is the keystroke level model. Compared with the deep cognitive understanding required to describe problem solving activities, the human motor system is well understood. Keystroke level model uses this understanding as a basis for detailed predictions about users' performance. So its main focus is at unit task within interaction. The execution of simple command sequences. Those will take typically not more than 20 seconds. It works at the lowest level of original GOMS model, that is the goals, operators, methods and selection model. For example, consider that you are using a search and replace feature or changing the font of word. It does not extend to complex actions such as producing a diagram. The assumption is that these more complex tasks would be split into subtasks as we do it in the form of GOMS model before the user attempts to map them into physical actions. The task is split up into two phases as we have already seen that it works for acquisition and then execution of the task. Acquisition of the task here is done when the user builds a mental representation of the task, and execution of the task is using the system's facilities. So KLM only gives prediction for the execution of the task activity. It is majorly concerned with the prediction of the execution part. Okay, execution of the task activity. During the acquisition phase, the user will have decided how to accomplish the task using the primitives of the system, and thus during the execution phase there is no high level mental activity. The user is effectively expert. So we can say that KLM is related to GOMS model and can be thought of as a very low level GOMS model where the method is given. So here the model decomposes the execution phase considering that into 5 different physical motor operators, a mental operator and a system operator. So there are different operators which are provided over here. So K representing the keystroking over here, actually striking the keys including shifts and other modifiers. P means pointing or moving the mouse or similar devices at a target. H means homing, which is switching the hand between the mouse and the keyboard. D is for drawing lines using the mouse. And M, that is representing the mental preparation, is used for a physical action. R is nothing but the response or the system response, which may be ignored if the user does not have to wait for it, as in case of copying or copy typing. The model decomposes the execution phase into different physical motor operators, mental operators and a system response operator as we saw it over here. Times are empirically determined over here. It works on the empirical model. So here the times are determined in the form saying time for keystroking, time for pointing, for homing, for the response time and so on. So let's proceed further with the KLM model. The times for the other operators are obtained from the empirical data, and the keying time obviously depends on the typing skill of the user, and different times are thus used for different users. Pressing a mouse button is usually quicker than typing, specifically if we are using the for two-finger typist. Imagine we are using a mouse based editor. If there is a single character error, we'll point at the error, delete the character and retype it, and then return to our previous typing point. This is decomposed as follows. The mental model is probably the most complex part of KLM. The user is assumed to have decided what to do and how to do it. The mental preparation is thus just the slight pauses made as the user recalls what to do next. There are complicated heuristics for deciding where to put the M operators. That means the operators which are based on the mental operators rather. But they all boil down to the level of chunking. For example, if the user types a word or a well-known command name, this will be one chunk and hence one require only one mental operator. The physical operators times all depends on the skills of the user. So there are different operators which are there. In this example, we can see that if you're supposed to move a hand to the mouse, it will be termed as H. The position mouse after the character which was left would be PB. Returning to a keyboard would be H. Deleting a character would be probably moving to the character and then deleting the character, and so on. The model predicates the total time taken during the execution phase by adding the component times for every activity. For example, if the time taken for one stroke is Tk, then the total time doing keystrokes is 2 of small tk. Okay. Now, there are some points which are expected to be known for KLM. The predictions made by KLM are only meant to be an approximation, and thus reasonable guesses about levels of expertise are enough. Here we say that basically it works at the unit task at the lowest level. The power of KLM lies in comparison. Given several systems, we can work out the methods to perform key tasks and then use KLM to tell us which system is the fastest one. So it is basically used, or it is going to work the best if we are using it for some comparison. The system need not even exist. So from a description of a proposed system, we can predict the times taken for task as well as comparing systems. We can compare methods within a system. This can be useful in preparing training materials, as we can choose to teach the faster method. We can see that from this particular point, it is also useful for some of the systems which are not actually prepared and can be used for training materials as well. KLM is one of the few models capable of giving accurate quantitative predictions about performance for a small range of applications. It tells about the micro interactions but not about the larger scale dialogues, as it works on the unit tasks. Coming towards the next point, let's see what are the architectures, or I would say the cognitive architectures. The formalisms we have seen so far have some implicit or explicit model of how the user performs the cognitive processing involved in carrying out a particular task. For example, we would say that Gom's model is about the concept of taking a problem and solving it by divide and conquer method or by using sub-goals. The CCT model assumes the distinction between long and short-term memory, with production rules being stored in long-term memory specifically and matched against the contents of short-term or the working memory to determine which particular production rule is to be fired. The values for various motor and mental operators in KLM were based on the model human processor architecture of Card, Moran and Newell. Another distinction is between the linguistic levels. So we saw over there we talked and saw about the semantic, synthetic and the lexical analysis as an architectural model of the user's understanding. The architectural assumptions are central to the description of cognitive modeling that these approaches offer. There are interesting differences of emphasis between these architectural models and the previous models. The hierarchical and the linguistic models also we have studied. Notations tend to assume perfect dialogue to the user's part. For the architectural models, here the prediction and understanding of error is central to their analysis. So, over here, problem spaces is the one which we are going to learn in much depth. What is problem space? Rational behavior is the behavior that is intended to achieve a specific goal. This element of rationality is often used to distinguish between intelligent and machine-like behavior. In terms of artificial intelligence, a system with rational behavior is referred to as a knowledge level system. A knowledge level system contains an agent behaving in an environment who has knowledge about itself and its environment, including its own goals, and can perform certain actions and sense the information about its changing environment. General computational model for a machine which is not rational, it is common to describe a problem as the search through a set of possible states from some initial state to a desired state. So it is going to talk mostly about the states. The machine architecture allows the definition of the search or the problem space and the actions that can occur to traverse that space and terminate after reaching the desired state. So once we have reached the final state, we have to terminate. The machine does not have the ability to formulate the problem space and its solution, as it has no idea of the goal. It is the job of the programmer to understand the goal and so define the machine to achieve it. The problem space model is based on the problem solving work of Newell and others. This model basically consists of set of states and a set of operations that can be performed on these states. So it consists of two states we would first of all see. The first one says the current operator is chosen based on the current state and then it is applied to the current state to achieve the new state. So it's going to talk about the different states. The problem space must represent rational behavior, which we already saw, and so it must characterize the goal of the agent. A problem space represents a goal by defining the desired states as a subset of all possible states. Finding a sequence of operations that form a path within the state space from the initial state to one of the desired states whereupon the successful termination occurs. Along with that, it consists of 4 operations or 4 activities we would say within the problem space. The 4 activities include the first one, goal formulation. So the perception that occurs at the knowledge level is performed by this process, which creates the initial state based on observations of the external environment. The operation selection process selects the appropriate operation at a given point in time because it is deemed the most likely to transform the state in the problem space to one of the desired states. Hence, rational behavior is implied. The operation selection process suggests an operation that can act on the state and transform it closer to the desired state. The operation application process executes the operation, changing the current state and surrounding the environment. And finally, the goal completion process. If the new state is a desired state, so we have reached to the end, then the goal has been achieved and the goal completion process reverts the agent to inactive. The real power of the problem space architecture is basically in using at places where recursion is being applied. Thank you.